We shall discuss today two algorithms for primality testing. And before we see the algorithm, we need to collect some more basics from number theory. First, let us see what is the square root of 1 modulo n. That is the square root of 1 in the modulo n system. For every n greater than or equal to 1, 1 and minus 1 are square roots of 1 modulo n. That is easy to see because 1 and minus 1 when you square, you will get 1, no doubt. So, they are definitely square roots of 1 even in the modulo system, and they are called the trivial square roots of 1 modulo n. Let n be a positive integer and x be an integer such that x is neither 1 nor minus 1, but x square is congruent to 1 modulo n. That means x is a square root of 1 in the modulo n system and x is not 1 or minus 1. Then x is called a non-trivial square root of 1 modulo n. Examples: take n as 35 and x as 6. When x is 6, x square is 36, and in the modulo 35 system, which is 1, because when you divide 36 with 35, 1 is the remainder. So, you can see that 6 is a non-trivial square root of 1 because 6 square is giving you 1. Another example, take n as 63 and x as minus 8. If you look at the square of minus 8, it is 64, which is congruent to 1 mod 63. So, in this case, when you square x, you are getting 1 in this modulo system, and hence minus 8 is a square root of 1, which is a non-trivial square root. So, I hope you are getting what are non-trivial square roots for a number system. Now, we can have a theorem. If P is an odd prime, meaning P is a prime number which is not 2, and E, which is going to be an exponent, is any natural number other than 0, then the equation x square is congruent to 1 mod prime raised to an exponent in this set has only two solutions for x. The only values of x satisfying this equation when P is prime is x is 1 and x is minus 1. So, when P is prime, you will only have trivial square roots for 1, and the proof is left as an optional exercise. And as a corollary for the theorem, we can say that if 1 has a non-trivial square root in the modulo n system, then that n must be composite, because from this theorem we know that when you substitute E as 1, when P is a prime, the equation x square is congruent to 1 mod P raised to 1 is P, has only the trivial solutions for x, 1 and minus 1. So, if you can find that 1 has a non-trivial square root in the modulo n system, then it must be composite, because otherwise, because if you have a non-trivial square root, then this number cannot be prime because of this theorem. So, this is a nice result which we can utilize for primality testing. That is, if we can find that there exists a non-trivial square root for 1 in a modulo n system, then n must be composite. Example, why? Because there exists a non-trivial square root of 1, that is why. Now, we need to talk about Bayes' pseudoprime in the first algorithm for primality testing that we are going to discuss. So, for that, let us see what is Bayes' pseudoprime. It is defined as follows. A number n is called a base A pseudoprime if n is composite. See, you are defining it only when n is a composite number. It is not meaningful when it is a prime number. So, n is a composite number satisfying this equation. What is the equation? A to the power n minus 1 is congruent to 1 mod n. And not that if n is prime, this equation is always true. That is what we know from Fermat's theorem. But satisfying this equation is not sufficient to conclude that n is prime. But if n is prime, it is a necessary condition but not a sufficient condition. And n is called a Bayes pseudoprime if when you take an element A in the modular system Zn, and if you compute its power with n minus 1 as the exponent, then you are getting 1 as the result in the modulo n system. But it is not a prime number, it is a composite number. Such composite numbers are called Bayes pseudoprime. For example, 341 is a Bayes 2 pseudoprime. Here A is 2 because it is a composite number. You can write it as 11 multiplied by 31 is 341. It is not a prime number, it is a composite number. And here A is taken as 2. 2 to the power 340 can be verified as congruent to 1 mod 341. See, it is of the form A raised to n minus 1. When n is 341 and A is 2, it is of the form A raised to n minus 1 is congruent to 1 mod n. That is the form. So, just try to remember what are pseudoprimes. They are not really primes, but looks like satisfying the Fermat's theorem. Now, we can see how we can do primality testing. It is the problem of checking whether a given number is prime or not. A naive algorithm can check whether a number is prime by searching for a divisor for that number in this set from 2 to root n. These are the possible divisors other than 1. You see whether any of these are divisors of n. If none of them are divisors, then it is a prime number. Otherwise, it is not a prime number. If you have a divisor from this set, then n cannot be prime. This is a very common logic for primality testing, but it is a very costly algorithm. The complexity of this algorithm is theta of root n because you have to inspect each element in this set to see whether it is a divisor, and which is in fact exponential in the length of n, which is the number of bits to represent n. You know that if there are n bits, you can represent up to 2 to the power n. That is the maximum value which can be represented, and that is why it is called an exponential algorithm. Exponential in the length of the binary string representing n. Now recall Fermat's theorem, which tells you that for any element A in this multiplicative group, a to the power p minus 1 is congruent to 1 mod p for all prime p. This is Fermat's theorem. I hope you remember it, otherwise for such mathematical basis you go back and see the previous lecture. You know that Zn is this set, the modulo n integers, and the notation Zn plus represents all the numbers in this set except 0. If you take out 0, you call it as Zn plus. And Zp plus is nothing but Zp star. You know that in Zp you have all the numbers from 1 to n minus 1 when p is prime. Given an odd number n, if you can find an a in this set such that a to the power n minus 1 is not congruent to 1 mod n, then from Fermat's theorem we can conclude that it is a composite number, because if n is a prime number, a raised to n minus 1 must be congruent to 1 mod n. So if you can come up with a number here a such that a to the power n minus 1 is not congruent to 1 mod n, then you can conclude that n is a composite number. So this is giving you another logic for solving primality checking. So you come up with an a, you find a to the power n minus 1 in the modulo n system, for which we have an algorithm for modular exponentiation. You do that and then see whether you are getting 1 as the result or not. If it is not 1, then it must not be prime, because if it is prime it must be 1. So we are getting a logic, and with that we can have an algorithm. This is an algorithm in the textbook, I just copied it. The algorithm is named as pseudoprime, and why is it named as pseudoprime, that we will see later. And what is it doing? The same logic that we derived. It finds a to the power n minus 1 modulo n, and a is applied as 2. A is fixed, which is given as 2. It can be any number in Zn plus, but this algorithm fixes it to 2. So it computes 2 to the power n minus 1 modulo n, and which is not congruent to 1 mod n, then we found in the previous slide that it must be composite, because we know from the Fermat's theorem that if it is prime, then this must be 1. If it is not 1, surely it is not prime. It is a composite number. And suppose it is 1, it may not be a prime number. Even then the algorithm makes a claim that it is prime. So the algorithm is not always correct. This answer may be wrong. It is just an assumption. Oh, just say that it is prime. May not be correct. If it returns composite, then the decision or answer is correct, because we know from the Fermat's theorem. But if it returns as prime, it may not be correct. When it fails is when n is a base 2 pseudoprime. You know that a base 2 pseudoprime is a composite number such that 2 to the power n minus 1 is not congruent to 1 mod n. Is congruent to 1 mod n. This is the definition of pseudoprime. Okay, in that case it will fail, because if it is not congruent to one mod n, it is sure that it is a composite number. But if it is congruent to one mod n, it may be a prime number or may not be a prime number. In this case, if it is not a prime number, then by definition of base A pseudoprime, it is a base 2 pseudoprime. So in that case it will fail. I hope you remember the definition of base A pseudoprime, otherwise go back and see what is it. Okay, so it fails if n is a base 2 pseudoprime, but the algorithm is almost correct because there are only very few base 2 pseudoprimes. Now the question here is, can we rectify this error by considering other elements from Zn plus? Here we are taking A as 2, but A can be an arbitrary element in Zn plus. Now the question is, by selecting a different number as A from this set, can you rectify this issue? Maybe you go for all the elements, finitely many elements, only n minus 1 elements are here. So you go for all those numbers as A, then can you rectify this problem? The answer is no, you cannot, because there are composite numbers called Charmichael numbers, such that for a Charmichael number, whatever be the A that you are taking, A to the power n minus 1 will be congruent to 1 mod n, but the number is composite, so it doesn't help. For Charmichael numbers, it doesn't matter whatever A you take, you will get A to the power n minus 1 as congruent to 1 mod n. So these are very difficult numbers to check. They satisfy this Fermat equation for all values of A in this set, but still it is non-prime. So you cannot completely rectify this problem. Okay, I hope you are getting. Examples of Charmichael numbers are here. Now we are going to see an improvised version of that algorithm proposed by Miller and Rabin, and the algorithm is named as Miller Rabin primality test. And the basic idea is to reduce the error rate. I told you that it cannot be eliminated completely because of the existence of Charmichael numbers, but otherwise you can. So it tries to reduce the error rate in the pseudoprime algorithm, and it do two modifications. So this is the test that we are applying, and if you can find an A such that this is not satisfied, A raised to n minus 1 is not congruent to 1 mod n, you can declare that it is composite, right? So the first modification or improvisation is, they do it for a number of elements in this set, not just for 2, but for a number of elements in that set. And not that this will not allow you to completely rectify the error even if you take all the elements, because Charmichael numbers are those composite numbers for which the equation will be satisfied for all elements in this set, but still non-prime. And another improvisation is making it faster. While computing the modular exponentiation, if you recall from the previous lecture, the major operation that we did in the modular exponentiation is squaring, repeated squaring. Now what it do is, in between when it tries to find the modular exponentiation, in between if it finds a non-trivial square root for 1, then it declares that it is a composite number. We can see how is it doing, and here is the lemma that will help us to get that algorithm. Statement is a little lengthy, but it is very easy to prove. If n is a positive odd number, so it is a positive number and an odd number which is not 1, then the claim is that there exists a natural number t which is not 0 and an odd positive integer u such that n is an odd number, so n minus 1 is an even number. N minus 1 can be written as 2 to the power t multiplied by an odd number u. The proof is left as an exercise, but it is very easy. An example itself is enough. You take n as 73, which is a positive odd number other than 1. And what is n minus 1? It is 72. So I am claiming that 72 can be written as 2 to the power t for some t multiplied by an odd number. So what you can do here for the proof is, you can generalize it, because it is an even number, n is an odd number, so n minus 1 is guaranteed to be an even number. So you can write it as 2 multiplied by something. Here it is 2 multiplied by 36. Now if this is an odd number, you can stop, but this is still an even number. So again you can apply the same technique, 2 then followed by 2 multiplied by 80. Here again you are getting an even number. You have to do it until you get here an odd number. Now you can say that it is 2 multiplied by 9. So now you see you are getting it as 2 to the power 3 multiplied by 9. So it is in this form, and this technique you can apply for any even number. You will get 2 into 2 into 2 into 2 t number of times for some t multiplied by an odd number. Now a nice thing about the binary representation of this form is that here this number is 72 and this is the binary representation, say 2 to the power 6 plus 2 to the power 3, which is 72, and observe that it is nothing but, if you look at the binary representation of 9, it is 1001, right? And this is nothing but the binary representation of this odd number followed by these many zeros. That you can prove in general. Okay, what I am claiming is that if you look at the binary representation of 2 to the power t multiplied by u, when u is an odd number, it is nothing but the binary representation of u followed by t zeros. You just observe it from here, but you can generalize, and in fact you can prove it. Now what we said is that if n is an odd number other than 1, then n minus 1 can be written as 2 to the power t multiplied by u, where u is an odd number. So n minus 1 can be written as 2 to the power t multiplied by u is what this lemma is saying. That is what I did here. Okay. Now this I can write as a to the power u the whole to the power 2 raised to t. Okay. A to the power mn is nothing but a to the power m the whole to the power n. That is what I am applying. Okay, thus you see that what we have to actually compute is a to the power n minus 1, which can be written as a to the power u. So what is that u? Because n minus 1 can be written as 2 to the power t into u, that is this u. And you first compute a to the power u, okay, and then you do repeated squaring for t number of times. What you are getting is this quantity, and this is nothing but a to the power n minus 1. So what we observe is that we can find a to the power n minus 1, this is modular exponentiation, by repeated squaring of a to the power u. Okay. Now with that we are going to see the Miller Rabin test for checking primality, and it makes use of a sub procedure which is to see whether a is an element of Zn plus witnessing the compositeness of n is what it is checking. So what is it doing is, from the previous lemma you know that if n is a composite number, if n is an odd number which is not 1, and then you can get a t and an odd number u such that n minus 1 is nothing but 2 raised to t into u. This is what the previous lemma told us. Okay, so you obtained t and u such that n minus 1 can be written as 2 to the power t multiplied by u. And previously we observed that then you can find a to the power n minus 1 by repeatedly squaring u, right? And so what is u? U is actually a to the power u mod n. So initially you have to find a to the power u mod n, and then you have to do repeated squaring on the result. So we are calling the modular exponentiation algorithm that we learned in the previous lecture to find a to the power u mod n. And from the previous slide we saw that once you find a to the power u mod n, then you do repeated squaring of the result. How many times? T number of times. That is what this is doing. So you are taking that result a to the power u mod n into x0, then you are squaring it successively t number of times. That is, for I is equal to 1 to t, first you are finding x1 is equal to x0 square mod n. Then you will find x2 is equal to x1 square mod n. So you are doing it for t number of times. And this is one improvisation. When in between, when you are in the process of finding a to the power n minus 1 mod n, you are checking whether you are finding a non-trivial square root of 1, and suppose that the square you are obtaining as 1 and the previous number which is squared is neither 1 nor minus 1. And not that in the modulo n system minus 1 is represented as n minus 1, which is a non-fact. If you are not able to understand that, you refer and see that in the modulo n system minus 1 is represented as n minus 1. So xi minus 1, the previous number is neither 1 nor minus 1, but when you squared it you got 1 as the result. That means xi minus 1 is a non-trivial square root of 1. Then from the Fermat's theorem you can conclude that the given number n is a composite number, and that is why you are telling that it is a composite number. When it returns true, it says that it is a composite number because A is a witness for the compositeness of n, because here you got an x which is actually xi minus 1 such that x is neither minus 1 nor 1, not that minus 1 in modulo n system is represented as n minus 1, and x square, when you find the square of that, you are getting 1 as the result. That means x is a non-trivial square root of 1, and hence from Fermat's theorem it must be a composite number. Okay, suppose you finish this loop, then at the end you are getting a to the power n minus 1 in xt, and from Fermat's theorem it must be congruent to 1 mod n if n is a prime number. But here you are checking whether it is not 1. If it is not 1, then Fermat's theorem we know that n must not be prime, so you are saying that it is a composite number. I hope you are getting it. Otherwise please watch it again. For the interest of time I am moving on. So we verified that it returns true if A is a witness for the compositeness of n. Now we are going to see what is this Miller Rabin primality test. What is it doing is, it just takes a random number between 1 and n minus 1, that is uniformly at random. It picks an element of zn plus, and it checks whether that element is going to witness the compositeness of n, the previous algorithm. And if it returns that it is composite, for sure it is a composite number. Otherwise, it goes back and takes the next A and continues. So, how many times that you can decide, you can pass it as an argument. That many times it uniformly at random it picks an element of Zn plus, which is A, and then checks whether that A is going to witness the compositeness of L. And after that it returns prime. And this result may not be correct, but very rare chance that it is returning a wrong result. So, this is Miller Rabin primality testing. So, today we have seen two algorithms for primality testing. Thank you.